Hey everybody, we are Team Gucci GAN, and this is our project on melody generation using a GAN. The main problem we're trying to tackle is generating cohesive melodies given an input sequence. This is pretty interesting because algorithmic music composition is an active field, and approaches are being undertaken both in academia and by actual musicians. This kind of work is important because musicians are always looking for new tools to augment their creative ideas, and currently there are several approaches to this problem, such as MIDINet, Google Magenta. Some of these results are pretty decent, but overall, it's a challenge to create realistic sounding music. It's also pretty difficult to objectively evaluate both generated music and music in general. For our approach, we adapted MIDINet on a new dataset and came up with a novel evaluation criteria that hopefully can be used for more consistent evaluation between music generation projects.
We are using the Pop 909 dataset as a real input data for model training. It contains 909 pop songs created by professional musicians in MIDI formats. For our model, we are only using the main melody track as input since we are focusing on melody generation. All the files are loaded with a time signature of 44 and a resolution of 24. After sanitizing, we are able to extract over 40,000 bars from the dataset.
So for our approach, we decided to use a deep convolutional GAN model, which was adapted from the original MIDINet paper. Some of the adaptations that we made was to increase the resolution of the notes that we were using as the data. This resulted in a 128 by 96, which actually allows us to represent more complex musical structures such as triplets and 30-second notes. We also performed greedy search on each of the outputs to produce a note at every time step. And for sequence generation, we would use a prior from the real data set and feed that to generate the next time step to generate the entire music. So for our model, we had the generator and discriminator model, and we treated the input data as an image, and we performed a convolution on that. And we also had the latent space with the noise and potentially a chord conditioner, and we used that to generate the image by doing a transpose convolution. Similarly, with the discriminator, we had an image convolution that would squash the output into a probability saying whether or not the image was real or fake.
To evaluate our results, the first method we used was a subjective user survey, where users were given an input sequence and had to identify whether it was real or fake and rate it based on rhythmic qualities, perceived melodic qualities, and the variety of notes in the sequence. For an objective evaluation, we used metrics from piano roll, which included the range of pitches in a sequence and the beat rate, and this can potentially give us some information about the rhythmic qualities of a sequence. So looking at our survey results, the users correctly identified which sequences were real with relatively high accuracy, but there were some inconsistencies. Like in some cases, we had put the same sequence in the survey, and some users actually rated them differently. Looking at objective metrics, the fake samples received high scores for beat rate, and fake samples tended to have a greater number of pitches and larger pitch ranges than the real samples. So here we have the number of real versus fake sequences that were correctly predicted. Users identified the correct prediction 69% of the time. Real samples were rated higher for melodic content than fake samples on average. So this kind of makes sense, especially given that fake samples had more pitches and wider pitch intervals. So it's totally possible that some of those did not correspond to what was perceived as being within a scale or a certain key. Both samples were rated pretty highly for rhythm, and this seems to correspond with the beat rate metric that we calculated. So here's an example of one of our generated music sequences with a notated score and MIDI representation.
So what did we learn from this experience? Well, for one thing, we were able to recreate MIDINet from scratch. We were able to adapt this model to actually increase the resolution as well, to provide a richer output of music. And we also expanded this architecture to 2 novel datasets. Lastly, we were able to evaluate the model's output with new metrics, both being subjective and objective metrics. So some of the few takeaways that we had was that working with GANs can be pretty challenging. Some of the problems we faced were dealing with convergence instability and also mode collapse. We also had problems trying to interpret the loss we saw from the GAN from a musical quality perspective. So we couldn't necessarily predict the quality of music that we were going to get based off the loss that we were actually seeing in the GAN model. Lastly, we note overall that music generation still remains a difficult task to evaluate and perform. So subjective music critique can often be unreliable and inconsistent, as we saw from our survey data. And also the standard metrics cannot necessarily predict the quality of music simply by looking at the measures.
So just for fun, we sent one of our generated sequences to a music producer. I'll play you a snippet of the original and the version that he came up with. Thanks for watching.